In southern China, deep underground, hangs a huge glowing sphere of liquid.
The solution for how do we measure these neutrinos is to build very, very big detectors.
We try to measure neutrino mass differences by using this detector to know that which neutrino is heavier, which one is lighter.
Around it, thousands of light sensors wait for the faintest flashes. This is Juno, the Jiangmen Underground Neutrino Observatory.
Every single photon can generate a pulse with 10 million electrons, and then the signals will be taken out by cables to electronics, and we store them in the computer to do analysis.
Built to study ghost-like particles called neutrinos. Here's why this detector is such a big deal. What are neutrinos? Neutrinos are some of the most mysterious and least understood particles in the universe, yet they are everywhere, so abundant and so fundamental that modern physics would collapse without them. To understand why China is building a massive detector like Juno, you first have to understand what makes these particles so strange. Neutrinos are elementary particles, meaning they are not made from anything smaller. They belong to a category called leptons, which also includes electrons. But unlike electrons, neutrinos carry no electric charge. That neutrality is the reason behind their name. Neutrino essentially means little neutral one. Because they have almost no mass and no charge, they barely interact with matter at all. That single fact shapes everything we know and don't know about them. Every second, trillions upon trillions of neutrinos stream through your body, your house, the ground below you, and even through entire planets, without slowing down or hitting anything. If a solid wall of lead were a light year thick, far thicker than the distance between the sun and its closest neighboring star, most neutrinos would still pass right through it as if it weren't there. This incredible ability to slip through matter makes neutrinos extremely difficult to detect. Scientists have spent decades designing bigger, more sensitive detectors just to capture a tiny fraction of these ghostly particles. Neutrinos come from some of the most powerful natural processes in the universe. They are created in staggering quantities inside stars, produced as a byproduct of the nuclear fusion reactions that make the sun shine. In fact, most of the neutrinos that pass through us originate from the sun's core, created in unimaginable numbers during the fusion of hydrogen into helium. Neutrinos are also produced on Earth, especially inside nuclear reactors, where the decay of radioactive isotopes spits out steady streams of them. Particle accelerators can generate neutrinos as well, allowing scientists to study them under controlled conditions. But perhaps the most dramatic neutrino factories in the cosmos are supernovas, the massive explosions that destroy dying stars. When a star collapses and detonates, a huge burst of neutrinos is released, carrying away the majority of the energy of the blast. In fact, when supernova 1987A exploded in the Large Magellanic Cloud, the first signal we detected on Earth wasn't light from the explosion. It was a short burst of neutrinos arriving hours earlier, passing straight through the universe long before the shockwave made the collapsing star visible. Another reason neutrinos are such a scientific obsession is that they challenge our understanding of physics. According to the Standard Model, neutrinos should have zero mass. For a long time, that was the accepted truth. But in the late 1990s and early 2000s, experiments in Japan and Canada discovered something revolutionary. Neutrinos oscillate, meaning they switch between different flavors: electron neutrinos, muon neutrinos, and tau neutrinos, as they travel. This flavor-changing behavior is only possible if neutrinos have mass, even if it's extremely small. That discovery was so important that it earned the 2015 Nobel Prize in Physics. But here's the twist. We still don't know exactly how much mass neutrinos have, nor why they have it at all. The Standard Model, our best theory for how particles and forces work, simply doesn't explain it. Physics has to be expanded to make sense of them. Neutrino oscillations also reveal something deeper. The different types of neutrinos have different masses, but scientists don't know the order of those masses. This question is known as the neutrino mass hierarchy. Are there 2 light neutrinos and 1 heavy one? Or 2 heavy and 1 light? This might sound like a small detail, but the answer has enormous consequences for cosmology. particle physics, and our understanding of how the universe evolved. It affects how neutrinos shaped the early universe, how matter might have outweighed antimatter after the Big Bang, and how physics might look beyond the standard model. All of these mysteries come together to explain why scientists need giant detectors like Juno. Detecting neutrinos requires enormous volumes of extremely pure liquid or ice, incredibly sensitive sensors, and deep underground facilities to shield out background noise. Juno, with its immense underground sphere and ultra-precise instruments, is designed specifically to crack some of the biggest remaining puzzles about these ghost particles. Understanding neutrinos means understanding some of the most fundamental laws of nature, and possibly discovering entirely new ones. How Juno is built. To understand why the Jiangmen Underground Neutrino Observatory, JUNO, is one of the most ambitious scientific instruments on Earth, you have to start with the scale of the challenge it faces. Neutrinos barely interact with matter. They stream through planets, stars, and people as if nothing is there. To detect even a handful of them, scientists must build detectors that are unimaginably large, incredibly sensitive, and almost perfectly shielded from background noise. Juno is China's most advanced attempt to solve this engineering puzzle, and it stands among the largest and most precise neutrino experiments ever built. At the heart of Juno is a massive spherical detector, a transparent acrylic ball roughly 35 meters in diameter, suspended inside a cavern deep underground in Guangdong province. This enormous sphere holds 20,000 tons of liquid scintillator, one of the purest and cleanest petrochemical fluids ever produced at an industrial scale. Liquid scintillator is crucial because it emits extremely faint flashes of light when a neutrino interacts with one of its atoms. The interaction rate is tiny, but with such a tremendous volume, Juno can collect enough data to extract meaningful patterns about neutrino behavior. The acrylic sphere itself is a feat of engineering. Its walls must be strong enough to withstand the enormous hydrostatic pressure created by the thousands of tons of fluid inside, while also remaining optically transparent and chemically stable for decades. Any contamination, even in trace amounts, can ruin the experiment, because impurities can absorb light or mimic the faint flashes that neutrinos produce. That's why the scintillator is purified through multiple distillations, water extraction, and gas stripping processes before being sealed into the detector. Surrounding the acrylic ball is another essential component, an array of about 18,000 large photomultiplier tubes, PMTs, plus an additional set of smaller PMTs for added precision. Photomultiplier tubes are ultra-sensitive light detectors capable of spotting a single photon. When even the faintest flash occurs inside the scintillator, the PMTs pick it up, amplify it, and send the signal to Juno's central data system. These are not ordinary sensors. They must operate continuously for years with minimal maintenance. Their timing precision is measured in nanoseconds, because the exact pattern of arriving photons is what allows scientists to reconstruct where and when a neutrino interaction occurred. The PMTs are arranged in a tight geodesic structure around the sphere, forming almost a complete cocoon of detectors. This dense coverage, roughly 75% optical coverage, one of the highest in the world, is what gives Juno its unprecedented energy resolution. In simpler terms, Juno can measure the energy of incoming neutrinos more precisely than any detector before it. That precision is what allows physicists to determine the neutrino mass hierarchy, one of the biggest unanswered questions in particle physics. Which type of neutrino is heaviest, and which is lightest? Outside the PMT layer is another protective component, a water Cherenkov detector, essentially a huge pool of purified water that surrounds the entire central sphere. This extra layer serves multiple purposes. It shields the detector from natural radiation coming from the surrounding rock, and it also functions as a secondary detector to tag cosmic muons, fast-moving particles created in Earth's upper atmosphere. Even with Juno located hundreds of meters underground, cosmic rays still make it through the rock. If they aren't detected and filtered out, their signals can be confused with neutrino events. The Cherenkov light produced when muons pass through the water helps Juno identify and ignore these intruders. Above all these layers sits an additional top tracker system, designed to monitor cosmic particles entering from above. Every part of Juno is built with redundancy in mind. Since all neutrino interactions are rare, every false signal removed is a major win for accuracy. The underground location of Juno is also essential. It is housed in a massive cavern beneath a mountain to block as much cosmic radiation as possible. The facility includes clean rooms, calibration systems, power infrastructure, and data pipelines capable of handling enormous volumes of information. A detector as sensitive as Juno requires regular calibration, so scientists use lasers, radioactive sources, and LED systems to ensure that every part of the instrument is measuring light correctly. Even tiny temperature changes can affect the detector's performance, so the entire environment must remain stable. Beyond the hardware, Juno's design also depends on advanced computational modeling. When a neutrino finally interacts with the scintillator, it creates a specific flash pattern determined by physics. Juno's computers must reconstruct the energy, position, and type of neutrino from the timing and brightness of the photons collected by thousands of PMTs. This requires sophisticated algorithms and enormous computing power, effectively turning Juno into a giant 3D camera aimed at the invisible universe. Taken together, Juno is more than just a detector. It is a multi-layered, ultra-clean, ultra-precise scientific system built to capture some of the rarest events in nature. Every component, from the liquid at its center to the cavern around it, is designed to eliminate noise, maximize precision, and push neutrino science further than ever before. It is a massive engineering achievement whose construction reflects China's growing leadership in experimental physics and its commitment to solving one of the biggest mysteries of the universe. The neutrino mass hierarchy. Neutrinos are some of the most mysterious particles in the universe, and one of the biggest open questions in physics is something called the neutrino mass hierarchy. Even though neutrinos are incredibly light, so light that for decades scientists thought they had zero mass, we now know they come in 3 different flavors: electron neutrinos, muon neutrinos, and tau neutrinos. These flavors constantly change into one another in a process called neutrino oscillation, and that oscillation only happens if each type has a different mass. But here's the problem. While we know the differences between their masses, we still don't know the order of those masses. That ordering is what physicists refer to as the hierarchy. And Juno, China's massive neutrino observatory, was built with the precision needed to finally reveal which neutrino is the heaviest and which is the lightest. To understand the mass hierarchy, imagine 3 musical notes. You know how far apart they are in pitch, but you don't know whether the highest note is in the middle, the lowest is at the top, or whether the order is inverted. This is essentially the problem scientists face with neutrinos. There are 2 possible hierarchies: the normal hierarchy, where the electron neutrino has the smallest mass and the tau neutrino has the largest, or the inverted hierarchy, where the electron neutrino sits at the top and the tau neutrino is the lightest. The differences might seem tiny, fractions of an electron's mass, but knowing which ordering is correct helps physicists understand how neutrinos influence the evolution of the universe, how supernovas explode, and why matter exists in greater abundance than antimatter. Juno is positioned in a uniquely advantageous location for this challenge. The experiment sits roughly 53 kilometers away from 2 powerful nuclear reactor complexes, each producing billions of electron antineutrinos every second. These antineutrinos stream outward freely, barely noticing anything in their path, until a tiny handful interact inside Juno's enormous spherical detector filled with 20,000 tons of ultra-pure liquid scintillator. When a neutrino happens to collide with a proton, it triggers a faint flash of light, and the surrounding array of thousands of photomultiplier tubes captures that signal. This setup allows Juno to measure the energy of each neutrino with extremely high precision. And that precision is exactly what's needed. As neutrinos travel from the reactors to Juno, they oscillate, switching flavors at different rates depending on their energies and the mass differences between the 3 types. The subtle imprint of the mass hierarchy is encoded in tiny wiggles in the neutrino energy spectrum. These wiggles are incredibly delicate, almost like interference patterns on the surface of a calm lake disturbed by 3 invisible stones. Most detectors in the world can only see the broad shape of the spectrum. Juno, on the other hand, was designed to resolve the fine details that distinguish the normal hierarchy from the inverted one. Detecting these oscillation patterns is something like listening for a faint harmony hidden beneath a loud, droning sound. The oscillations from the different mass states overlay one another, and the spacing between the peaks and valleys slightly changes depending on which neutrino mass is heavier. Juno's job is to listen with unparalleled clarity. To do that, it needs exceptional energy resolution, something like distinguishing two musical notes whose frequencies differ by less than 0.1%. Achieving this required innovations in detector purity, light collection efficiency, and the manufacturing of one of the largest and clearest liquid scintillator volumes ever created. Solving the mass hierarchy isn't only a technical challenge. It has profound scientific consequences. If Juno can settle the ordering, it would shape the direction of future particle physics experiments, especially those studying CP violation in the neutrino sector, an effect that might explain why the universe contains matter instead of collapsing into energy at the beginning of time. Knowing the hierarchy also improves models of how neutrinos behave inside collapsing stars, making supernova simulations more accurate. When the next nearby supernova erupts, Juno's knowledge of the hierarchy will help interpret the neutrino burst that arrives hours before the explosion becomes visible. Another important reason the hierarchy matters is that it connects directly to the search for a hypothetical process called neutrinoless double beta decay. If neutrinos are their own antiparticles, this rare decay could occur, and it is more likely to be seen depending on which mass ordering is correct. That means Juno's results could help other major experiments worldwide decide how to tune their detectors, where to focus, and which energy ranges matter most in the hunt for this exotic signal. In essence, the neutrino mass hierarchy is not just a puzzle, it is a roadmap. Determining whether nature chose the normal or inverted hierarchy unlocks a deeper layer of the standard model and guides physics toward the next frontier. Juno, through its extraordinary design and massive scale, is the experiment positioned to provide the definitive answer. With enough data over the coming years, Juno's high-precision measurements may finally reveal which neutrino sits at the top of the mass ladder and why that ordering matters for everything from supernovas to the birth of the universe itself. If you enjoy seeing how strange particles connect to big cosmic questions, hit like and subscribe. Sharing this video helps grow a community of people who care about deep-cut physics. Supernovas and Earth's interior. Neutrinos are often described as messengers from places we could never see directly, and Juno is built to listen to two of the most important sources of those messages: exploding stars and the deep interior of our own planet. These two environments could not be more different. One is a colossal cosmic blast that briefly outshines an entire galaxy, and the other is the slow, hidden engine that powers Earth's crust, volcanoes, and magnetic field. Yet in both cases, neutrinos are the only probes capable of escaping their environments almost unscathed. By detecting them, Juno becomes not just a physics experiment but an observatory for events that traditional telescopes cannot reach. To understand the significance of Juno's supernova watching role, imagine a massive star nearing the end of its life. As the star's nuclear fuel runs out, its core collapses in a fraction of a second. Temperatures soar higher than anything achievable on Earth. Densities skyrocket, and atomic nuclei are torn apart. In that chaotic instant, the collapsing core releases an enormous flood of neutrinos, far more than the total light the star will emit during the explosion that follows. In fact, around 99% of the energy of a supernova is carried away by neutrinos, not photons. Because these particles interact so weakly with matter, they pass through the star's outer layers almost immediately, racing into space long before the explosion becomes visible in light. This is why neutrino detectors like Juno are often called early warning systems for supernovas. If a star were to go supernova anywhere in our galactic neighborhood, Juno would detect the burst of neutrinos hours before telescopes pick up the flash of light. A single supernova neutrino burst could produce thousands of events inside Juno, giving scientists a detailed timeline of what happened inside the dying star. That data would reveal the mechanisms behind core collapse, shock revival, neutron star formation, and even the possible birth of a black hole. Events like this are exceedingly rare. The last time neutrinos from a supernova were detected on Earth was in 1987. But if another occurs within the Milky Way, Juno would record the richest set of supernova neutrino data ever captured. Juno's capabilities do not stop at sudden cosmic catastrophes. It is also tuned to detect the much quieter and more persistent neutrino signals coming from beneath our feet. These are called geoneutrinos, and they originate from the radioactive decay of elements like uranium-238, thorium-232, and potassium-40 deep inside Earth's mantle and crust. These decays have been going on since the planet formed, and the heat they produce is responsible for driving plate tectonics, volcanic activity, and convection in Earth's mantle. However, scientists still debate how much of Earth's internal heat comes from these radioactive sources versus leftover primordial heat from the planet's formation. Geoneutrinos offer a way to answer that question. Because radioactive decay inside Earth consistently produces electron antineutrinos, detectors like Juno can measure how many are reaching the surface. By counting geoneutrino events and comparing them with models of Earth's composition, scientists can estimate how much heat the radioactive elements produce. Juno will be extremely sensitive to these particles thanks to its massive volume and high-precision energy measurements. Over time, it could help determine whether Earth's mantle contains more or fewer heat-producing elements than current geological models predict. Another intriguing application lies in using neutrinos to map Earth's internal layers indirectly. Different rock compositions and densities affect the rate at which neutrinos travel and how many interactions occur in the detector. While Juno cannot produce a full picture of the mantle or core by itself, its data will complement seismic observations. Together, these two methods could help answer questions about how heat flows through Earth, why some regions of the mantle are hotter or cooler, and how this affects the movement of continents and the behavior of volcanoes. This kind of neutrino geology is still a young field, but Juno is expected to be one of its major driving forces. Supernova neutrinos and geoneutrinos also help Juno in another subtle way, by providing natural calibration sources. The energies and timing of these neutrinos are predicted with remarkable accuracy by theoretical models. When Juno detects them, scientists can check whether the detector's energy resolution and timing accuracy are performing exactly as expected. This improves Juno's ability to fulfill its main mission, determining the ordering of neutrino masses, but it also strengthens its role as a multi-purpose observatory. Taken together, Juno's ability to detect neutrinos from both the distant cosmos and Earth's interior makes it one of the most versatile particle detectors ever built. A single supernova burst could reveal the life cycle of stars and the physics of extreme matter, while steady streams of geoneutrinos help explain the geological forces that make our planet habitable. For the first time, one experiment can explore two realms of science that rarely intersect: the explosive death of stars and the quiet heat beneath Earth's crust. Through Juno, both become part of the same story, one told not with light or sound, but with ghostly particles passing through the universe and through us. Juno in a global network. Juno is not just a single experiment working in isolation. It is part of a growing worldwide network of neutrino observatories that together form one of the most unusual telescopes humanity has ever built. A telescope made not of mirrors or lenses, but of detectors buried underground, under mountains, or beneath oceans, all listening for particles that barely interact with anything at all. While Juno's design and size give it unique strengths, its full scientific impact only emerges when it is considered alongside the other major neutrino experiments operating across the planet. In this way, Juno contributes to a global system that is gradually turning neutrinos into a new complementary channel for understanding the universe, parallel to electromagnetic astronomy, gravitational wave astronomy, and cosmic ray studies. Japan hosts one of the most famous neutrino detectors in the world, Super Kamiokande, a massive water Cherenkov detector inside the Mozumi mine. For decades, Super K has led research on neutrino oscillations and solar neutrinos, providing key evidence that neutrinos change flavor, a discovery that required neutrinos to have mass at all. Juno brings a different approach to the problem, using liquid scintillator rather than water, which gives it far higher energy resolution. By combining Juno's precision with Super K's long baseline and atmospheric neutrino studies, the global community can cross-check measurements that no single detector could verify on its own. Soon, Japan will also operate Hyper Kamiokande, an even larger successor that will deepen the synergy further, especially for supernova science. Across the world in Europe, another crucial partner is the Borexino experiment in Italy's Gran Sasso National Laboratory. Although Borexino has concluded data taking, it set the standard for ultra-low background neutrino detection, especially for solar and geoneutrinos. Juno builds on lessons from Borexino's extreme purification techniques and applies them at a vastly larger scale. Meanwhile, Europe is preparing for experiments like Orca and Arca, part of the KM3NET project in the Mediterranean Sea. These deep-sea detectors specialize in high-energy neutrinos coming from cosmic sources, giving the network sensitivity to vastly different energies and astrophysical environments. While Juno focuses on reactor, supernova, and geoneutrinos, the ocean-based detectors extend the global reach into the realm of neutrino astronomy at TV and PV energies. In North America, Fermilab's NOVA experiment and the upcoming Deep Underground Neutrino experiment, DUNE, provide another layer of global complementarity. NOVA studies neutrinos produced by accelerators, allowing scientists to probe oscillations over long distances with controlled beams. DUNE, once operational, will be one of the most advanced detectors ever built, capable of observing neutrinos from multiple sources, including supernova bursts with remarkable detail. Juno's high-precision measurements of reactor neutrinos will help constrain parameters that DUNE needs for its own analysis, especially those associated with the mass hierarchy and mixing angles. In return, DUNE's long baseline results help refine global fits that Juno contributes to, ensuring that systematic uncertainties shrink as more experiments intersect. This worldwide network becomes especially important for rare astrophysical events, such as supernova explosions. If a massive star collapses anywhere in our galaxy, detectors across Earth will receive a flood of neutrinos long before the first photons escape the stellar debris. Because neutrinos pass through matter without significant obstruction, they carry direct information from deep inside the collapsing core. Juno's exceptional energy resolution will allow it to reconstruct the time structure and energy spectrum of the burst with high precision. Another key benefit of this network is redundancy. Neutrino measurements are notoriously difficult because the signals are faint and the backgrounds numerous. No single detector can rule out all sources of noise or systematic error. However, when multiple detectors around the world observe the same phenomenon, whether it is a change in solar neutrino flux, a reactor neutrino anomaly, or a burst from a supernova, the results can be compared and cross-validated. This reduces the risk of misinterpreting statistical fluctuations or local background effects as new physics. Juno's high energy resolution helps improve global fits of neutrino oscillation parameters, offering a level of precision that other detectors can use as a benchmark. Together, these experiments mark the emergence of neutrino astronomy as a full-fledged branch of astrophysics. Telescopes that collect light provide one perspective. Gravitational wave observatories like LIGO give another, and neutrino detectors add a third, a view that reaches into places light cannot go. Juno is pushing neutrino science into a new era, but what hidden events in the universe will it reveal first? And how will these ghost particles rewrite what we think we know about space and Earth itself? If you enjoyed this breakdown, don't forget to like and subscribe for more deep space stories.